In this introductory video on data structures, we will examine the fundamental components of all data structures and how they can be represented, and then discuss how they are implemented in the Java collection framework. We begin with a discussion of the various components of every data structure. The same components are present in all data types, whether or not they are considered a data structure. These components can be divided into two primary groups, those that are abstract and those that are concrete. The abstract perspective is what a user of the data structure would need to know in order to be able to use it. The JavaDocs tool extracts this information from Java source code to create the API for any Java class. The first component of the abstraction consists of the signatures of all of the methods that correspond to each of the operations that can be performed on the data structure. The other abstract component is a description of the behavior of each operation, explaining, typically in English, the effect of performing the operation. There are two concrete components as well. The concrete components constitute the information that would be needed by the programmer who is assigned the task of writing the code that implements the data structure. The first concrete component is the representation. In our exploration of data structures, we will discover that every data structure can be implemented using a variety of different representations. In a Java class, the representation of a data structure consists of one or more instance variables of the class. Making these variables private is a good practice to ensure that the user of the data structure cannot directly modify them. The second concrete component consists of the implementation, which is the code in the method bodies. The required code will always depend upon and correspond to what representation has been chosen. The user of a data structure should not need to know about either of these concrete components. Separating the abstract components from the concrete ones promotes the construction of what is sometimes referred to as loosely coupled systems. The coupling between classes consists only of what is defined by the abstraction. A useful analogy is a loosely coupled audio system, in which one set of speakers can be replaced by a different set, provided both conform to the required specifications. In much the same way, in a loosely coupled software system, one implementation of a data structure can be replaced by another, provided both adhere to the same specifications, defined by the abstract components. To facilitate construction of these loosely coupled systems, we will use Java interfaces to define the abstract view of every data structure. We will also observe, when we examine the Java collection framework that contains many of the standard data structures, that they make extensive use of interfaces as well. Next, we look at data structures at various levels of abstraction. At the top of this diagram, we have the most concrete representation of all data structures. Ultimately, if we examine any data structure at the machine level, all data structures, just like any kind of data, is some bit pattern stored at some address. This level corresponds to how one would access data in machine or assembly language. At the next level of abstraction, the primary distinction is between a statically allocated block of memory, which is typically an array, or a dynamically allocated collection of nodes linked together, which is typified by a linked list. When we are programming in an imperative language like Java, ultimately we must choose between these two options. We will come to expect that most every data structure can be implemented in either way. When programming in a language that supports a more declarative approach, the details at the previous level are hidden. Instead, we can view data structures in terms of the connections of their components. A list being a structure where every component, except for the first and last, has exactly one predecessor and one successor. With a tree, each element has one predecessor, more often called the parent, but multiple successors or children. A graph is the most general, with each element having multiple predecessors and successors. All three can be represented as contiguous blocks of memory or linked structures. Finally, we arrive at the highest level of abstraction. Stacks, queues, and so on can be represented by a variety of structures at the level above. Keep in mind that this diagram is not an inheritance diagram in the usual sense, where each arrow defines an is-a relationship. Instead, they can be represented by relationships. For example, a set can be represented by a list, implemented as an array or a linked list. It can also be represented by a tree, specifically a binary search tree. Now let's consider which data structures Java implements and how they are organized. We refer to them as container classes because every data structure contains a collection of some type of elements. These classes are divided into two major groups. The first group are the collections. All the collections contain a single type of element. The fundamental operations they all share are the ability to add and remove elements, to check whether an element is in the collection, and the ability to iterate across all elements of the collection. The first of these collections are the lists. What distinguishes lists from other collections is that the elements are in a linear order, so it is possible to specify the position at which elements are added or removed, and to inquire what element is at a specific position. As we discussed previously regarding all data structures, there are two basic representations. The first uses an array, which is a contiguous block of memory. This representation is the array list. Although an array is the underlying representation, the size of the array can be increased if necessary. The second is a linked list, which is implemented using discrete nodes that are linked together. The way in which they are linked is what defines the linear order. Stacks are also linear collections, but the operations are limited to pushing on new elements or popping off an existing element at the top of the stack, which makes a stack a last-in, first-out data structure. There are two types of queues, those that behave in a first-in, first-out fashion, and those that are ordered according to some priority. Finally, sets are modeled after mathematical sets, which means they are not ordered and they cannot contain duplicates. Despite being conceptually unordered, one possible representation is to store them in a sorted fashion. The other major category of container classes are maps. Unlike collections, they contain pairs of elements, referred to as key-value pairs. The possible representation for maps are similar to sets, so it is possible to represent them sorted by their keys. This final diagram is a UML diagram that contains a portion of the interfaces and classes that are in the Java collection framework. This diagram is an inheritance diagram in which the arrows represent true is-a relationships. Not included in this diagram are the map classes previously mentioned. Sitting at the top of this hierarchy is the interface that all collections implement. It defines operations common to all collection classes. At the level below are three more interfaces. The leftmost one defines the operations common to all set representations. The middle one defines the operations common to all lists, and the one on the right defines operations common to both first in, first out, and priority queues. Moving down one more level, apart from the interface at the left, we now see the actual classes that contain concrete representations of the data structures. The hash set is an implementation of a set that uses what is called a hash table. The array list and vector are both array-based lists. Unlike most classes in this diagram, the vector class was included in a very early version of Java. Finally, on this level, the linked list implements both the list and the queue interfaces, whereas the priority queue implements the queue interface only. At the very bottom level, we see the tree set class, which is an implementation of a sorted set, which uses a balanced binary search tree. The linked hash set, which is a variation on a hash set, and the stack, which is a subclass of the vector class. As we study how many of these data structures are implemented, we will better understand how hash tables, binary search trees, and other underlying data structures are implemented.